Hello, everyone, and welcome to this explainer. I am absolutely thrilled to guide you through today's topic. We're diving right into how Python programs achieve something pretty remarkable: long-term memory. We'll be walking through Chapter 2 of our source material, focusing entirely on file handling in Python. We're going to trace the complete life cycle of a file, from its creation all the way to reading, writing, and navigating inside it.
To really understand why this matters, you've got to ask yourself, what if we want to store data permanently? We've all written programs that take an input, do some coding magic, and print out an output. But here's the catch. That output only exists while the program is actually running. The variables we use, they have a super short lifespan. The very second that execution stops, poof, the data is just gone. Imagine the sheer frustration of calculating complex data only to lose it the moment you close the window. So how do we store that input and generated output permanently so we can actually reuse it tomorrow or next week?
Here's our agenda for today. 1. Why we need files. 2. Text first binary files. 3. Opening and closing files. 4. Writing data to files. 5. Reading data from files. And 6. Navigating inside a file. Let's get to it.
Section 1. Why we need files, secondary storage.
In the real world, organizations process massive amounts of data. Think about employee records, inventory counts, or daily sales figures. You literally cannot afford to do the repetitive task of re-entering this data every single time a program runs. That is exactly where secondary storage devices come into play. So what actually is a file? A file is basically a named location on a secondary storage media where data are permanently stored for later access. Think of it as the ultimate bridge. It connects the temporary, fleeting thoughts of your computer's RAM during a program's execution to the permanent, stable environment of your hard drive.
Section 2. Text versus binary files. Knowing your materials.
Just like a construction worker needs to know if they're building with wood or steel, a programmer has to understand if they're handling text or binary. Let's compare them. Text files are highly structured sequences of characters. While internally they're still just sequences of bytes, zeros and ones, encoding schemes like ASCII or Unicode translate those bytes into human-readable characters. For instance, the ASCII value 65 represents the capital letter A. Text files also use a special end-of-line or EOL character, like a new line /n, to separate the lines. Binary files, on the other hand, also use zeros and ones, but they do not translate to ASCII text. They represent actual media, like images, audio, or executable programs. Because they aren't meant for human eyes, opening a binary file in a simple text editor will just show you a mess of garbage values. You absolutely need specific software to properly read them. Even a single bit change can completely corrupt a binary file.
To really highlight the nature of text files, the source material provides a fascinating exercise. If you type your name into a basic Notepad text file, the file size is incredibly tiny, literally measured in bytes. But if you type that exact same name into a Microsoft Word document, the size suddenly jumps up to kilobytes. Why is that? Well, because the raw text file only contains the ASCII equivalents of the characters in your name. The Word document, however, is packed with hidden metadata: author names, page settings, font sizes, creation dates. Text files are just as lightweight and raw as data gets.
Section 3. Opening and closing files. The doorway.
The crucial point here is that before we can read or write any of this data, we must first establish a link. We basically have to open a doorway between our Python program and the storage drive. We do this using Python's built-in open function. Using the syntax file object equals open a file name access mode, this function proves incredibly powerful. If the file doesn't exist, this statement can actually create a brand new empty file for you. It returns what we call a file handle or a file object. This object is your golden ticket. It has attributes that tell us basic information, like file.close to check its status, file.name, or file.mode. When opening a file, we have to pass in an access mode. This mode dictates exactly what operations are allowed and where the file offset position starts. For example, R opens the file as read-only right at the beginning. But look at W, the write mode. It starts at the beginning, but it will completely overwrite any existing content. If you want to keep your old data, you'd want to use A for append mode, which cleverly places the file offset position right at the end of the file. You can also add a plus sign, like R+ or W+, to enable both reading and writing simultaneously. Now, once you open a door, you really must remember to close it. You can explicitly use the close method on your file object, which is good practice to free up system memory and flush any unsafe data from the buffer to the permanent file. However, Python offers a safer, way more elegant alternative: the with clause. When you open a file inside a with block, Python automatically closes the file the exact moment your program exits that block, even if an unexpected error occurs. It's just a fantastic fail-safe.
Section 4. Writing data to files. Putting things inside.
Once your file is opened in write or append mode, you have two primary methods at your disposal to put things inside. The first is write, which takes a single string and places it in the file. Interestingly, it returns the exact number of characters it just wrote. The second is write lines all, which is absolutely perfect when you have an iterable sequence of strings, like a Python list, and you want to dump them all in at once. A critical takeaway here is that you must manually add the new line /n character at the end of your sentences if you actually want them on separate lines. Oh, and also, if you're trying to write numbers, like a student's test scores, you can't just write the integer directly. You have to first convert that numeric data into a string using the string function.
Looking at this output from a standard editor like Notepad, we see exactly how a sequence of strings passed through write lines translates directly into a normal document. Because the programmer remembered to include the new line /n characters at the end of the strings in their Python list, the text editor correctly interpreted those ASCII equivalents and displayed the text on beautifully separated lines. Section 5. Reading data from files. Taking things out. Okay, so Python provides 3 distinct ways to read the contents of a file back out. They sound super similar, so it's vital to memorize the subtle differences in how they return data. First, we have reading. You can pass it a number n to read exactly n bytes, or just pass nothing to slurp up the entire file as one giant string. Second is read line, singular. This reads just one complete line, up to and including the new line character. It's great for iterating through a file line by line using a loop without overwhelming your computer's memory. Finally, read lines, plural. This reads all the lines in the file and returns them formatted as a list of strings, with each line being a separate element in that list. After retrieving our data, we almost always want to manipulate it. Consider 2 distinct string methods here. If you have a line of text and want to examine every single word individually, you can use the split function, which separates the text at the white spaces into a list of words. On the other hand, if you want to keep full lines intact without the new line characters dangling at the end, split lines separates the text into full lines as list elements. It gives you incredible fine-grained control over how you parse your text. Section 6. Navigating inside a file. The advanced maneuver.
Up until now, we've read files sequentially from start to finish. But what if we want to access data randomly within the file? Well, Python gives us 2 fantastic functions for this: tell and seek. Think of reading a file like reading a physical book. The tell function simply returns the current integer byte position of your file object. It's literally like asking, hey, what page number am I currently on? Conversely, the seek function is your bookmark. It actively moves the file object to a specific byte position that you dictate. You command the program to jump to a specific spot so you can start reading or writing from exactly there. Let's look really closely at the seek function's syntax. FileObject.seek offset reference point. The offset is simply the number of bytes you want to move, but the reference point dictates where that movement actually begins. If the reference point is 0, which is the default, your offset is counted straight from the beginning of the file. If it's 1, you move relative to your current position. And if it's 2, you count backwards or forwards from the very end of the file. So seek 10.0 confidently jumps you to the 10th byte of the file, completely ignoring wherever you were previously.
And that brings us to the end of our chapter analysis. But I want to leave you with a really fascinating question directly from the margins of our source text. Does the seek function work in the exact same manner for both text and binary files? Think about it. Text files translate bytes using ASCII, whereas binary files are pure raw bytes. Does a 10-byte jump mean the same thing to both? It's a provocative question that I highly encourage you to experiment with in your own Python editor. Thank you so much for joining me on this structured journey through Python file handling. You now understand how to give your code a permanent memory. Keep coding, keep exploring, and I'll catch you in the next explainer.